Welcome to our session number 42. In today's session, we're going to be continuing our discussion in second order effects in MOSFETs. Specifically, this is in chapter 22. We'll be talking about charge and gate oxide, trapped interface charge, and then we'll go on to the Deal-Grove model of thermal oxidation. So all these three topics deal with gate oxide. And then we'll be finishing it off, hopefully, with threshold roll-off, a graphic representation of that, so-called Yau model, and if we have time, evolution of the Q inversion and the IV relation, which is basically just a summary and a review of some of the things we've been covering in the MOSFETs. Hopefully we'll get through about I hope more than half, maybe 2/3. We'll begin with a wonderful performance of I Feel Pretty from Leonard Bernstein's West Side Story, and we'll see you in about 3 minutes.
I feel pretty, oh so pretty. I feel pretty and witty and gay, and I pity any girl who's in me today. I feel charming, oh so charming. It's alarming how charming I feel, and so pretty that I hardly can believe I'm real. See the pretty girl in that mirror there. Who can that attractive girl be? Such a pretty face, such a pretty dress, such a pretty smile, such a pretty me. I feel stunning and entrancing, feel like running and dancing for joy, for I love my pretty, wonderful boy.
Have you met my good friend Maria, the craziest girl on the block? You know her the minute you see her. She's the one who is in an advanced state of shock. She thinks she's in love, she thinks she's insane.
La la la.
She isn't in love, she's merely insane.
It must be the heat or some rare disease.
La la la.
Or too much to eat.
Or maybe it's please. Keep away from her, said Porcino. This is not the Maria we know. Modest and pure, polite and
La
refined,
la la.
well-bred and mature, and out of her mind.
¡Miss América! ¡Ay, qué linda se ve! ¡Miss América, bravo! Speech!
I feel pretty, oh so pretty, that the city should give me its key. A committee should be organized to honor me.
La 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 la.
I feel dizzy, I feel sunny, I feel fizzy and funny and fine, and so pretty, Miss America can just resign.
La 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 la.
See the pretty girl in that mirror there.
What mirror where?
Who can that attractive girl be?
Which what? Where who?
Such a pretty face, such a pretty dress, such a pretty smile, such a pretty me.
Such a pretty me. Such a pretty me. Such a pretty me.
I feel stunning.
I feel stunning.
And entrancing.
And entrancing.
Feel like running.
Feel like running
for
and dancing
joy.
for joy.
For I'm loved by a pretty, wonderful boy.
Welcome back, and here are some of the topics we'll be covering in today's session. Looks like a lot of topics, but basically we're going to be concentrating on the first three, and they involve the gate oxide. This is this incredibly thin layer between the gate and the silicon surface. It's generally anywhere between 15 to 30 angstroms. That's 15 to 30 atomic layers, an incomprehensibly thin layer of silicon dioxide. So we're going to be talking about charges in the gate oxide, and then we're going to be talking about trapped interface charge, and then we'll be talking about how we grow this thermal oxide, the Deal-Grove model of thermal oxidation. And if we have any time, well, at the end, we may just touch upon one of these remaining topics. Okay, so let's look at charge in the gate oxide. Charge is almost always positive. It can be of two basic types, either mobile, which is shown in red, or fixed. The positive, the arrow pointing up would imply that it's positive. The interface charge exists, well, it exists at the interface between the oxide and the silicon. That can be included here. It's either positive or it could be negative. Fixed charge is generally positive. But one thing's for sure, whether it's positive or even negative, it's always bad. It always has a detrimental effect on device performance. And that's why we try as much as possible to eliminate it. And in modern fabrication facilities, because they are cleaner and because we take a lot of care, the detrimental effects have pretty much been negated. However, we study it because it's of historical interest, and there's a lot of interesting physics involved in it. So this is a cartoon of the oxide here, and it's definitely not to scale because the distance between the gate and the silicon is, as I say, maybe only 20 or 30 atomic layers. There are three types of charge, which we divide into two main categories. Mobile charge, which can move around. Its title is mobile. It can move. And fixed charge, which always exists at the oxide-silicon interface. It is possible to have fixed charge which exists inside of the oxide. We don't consider that. It's not terrible. It's kind of a boring effect anyway. So the mobile charge, the characteristic of the mobile charge is that it can move. The effect of the charge depends on its position, which in turn depends on the gate voltage. If, for example, the charge is positive and I have a positive charge on the gate, it's going to move to the oxide silicon interface. Negative charge on the gate will attract it to the gate. The fixed, specifically the interface charge, which is the more interesting one, its position doesn't change, but its charge density changes. In the case of the mobile charge, the magnitude of the charge is fixed, just its position changes. In the case of the interface charge, as we say, the position is fixed, but the magnitude of the charge depends on the position of the Fermi level. Okay, the other thing is one final note. Generally, we're always considering these charges to be impulses. I mean, heck, the whole distance is only 30 angstroms. So if we have this thing maybe 1 angstrom thick, then it's probably not going to change very much. And it makes things a little bit more complicated. We can get all the physics by considering an impulse of 0 thickness. And that's true for all of the charges that we'll be considering. Okay, now, up to this point, charge, of course, up to this point, charge is always associated with electric fields, and electric fields are always associated with band bending in the silicon. But until this point, it was voltage which was the independent variable. Voltage was the knob, specifically in a MOSFET. The gate voltage was the knob that we turned to produce a voltage between the gate and the silicon bulk. Charge was the effect of voltage. So charge was the dependent variable, voltage was the independent variable. Charge did not exist independently of voltage. But now we have a situation, and we're going to be considering mobile charge first, where the charge is the independent variable, and it's going to produce a change in voltage. So the change in voltage is going to be the dependent variable, and charge is the cause, voltage being the effect. So this is the equation, the standard equation that we had before, voltage being the independent variable, charge the dependent variable, and the proportionality constant, of course, was the gate oxide, C-ox. So now we have a situation where charge is the independent variable, voltage the dependent variable, but they're still related by the gate oxide. That doesn't change. So we should expect, or tempted to think that as the charge position changes, perhaps the capacitance will change, and therefore the voltage will change. But this is, well, I would say it's illogical. It's quite logical, but it's not what we observe. Well, then, let's go to the next plan B. We can say that at best, because the charge is essentially one-dimensional, we may be tempted to conclude that it shouldn't depend on the position of X at all. I mean, why should the voltage change dependent upon the charge being over here or over here if it's mobile charge? And that is also not what we observe. The charge position has a big effect on voltage changes. So let's look at some of the correct assumptions. We're going to be looking at threshold voltage, and we're going to assume that the structure is in threshold, and the addition, and that's what we're going to be looking at, the mobile charge. First, the mobile charge does not bring the structure out of inversion, and as we said before, the charges are impulses. In most cases, they are positive impulses. And charge balance, that's the next big factor, always applies. We must have charge balance between the charge on the gate, the charge on the oxide, and the charge at the silicon surface. So somehow this mobile charge is going to affect the charge that appears on the gate. We don't know if, well, we assume it's going to be positive, because if it's positive charge, it's simply going to add to the gate charge to give us a new value of gate charge. But the magnitude of that addition is the interesting question that we're going to answer now. And we leave over the possibility that it could, in fact, even subtract, although that's not terribly likely. So let's consider case one. Case one is where we have somehow this charge, we're not saying how, arrives at the gate oxide interface. And here it is. This is the mobile charge. This is the gate charge. And what we're conjecturing here is that the mobile charge simply adds to the gate charge, but because now the charge is greater than it was before the mobile charge, we would expect that the voltage would be greater, the gate voltage would be greater. More charge, more voltage, more charge. So we conjecture that there would be a new gate voltage, which would be equal to the new gate charge, and this should not have this apostrophe. Let me see if I can change that. Delete that. Okay, so that's better. We have now the new gate charge, QG prime, divided by C-ox, which will give us a new gate voltage, and it should be greater than the old gate voltage. But that can't be, because the gate voltage is an independent variable. The gate voltage depends on what I choose to make it. So the gate voltage cannot change. What happens is now that the mobile charge must subtract from the new gate charge so that the gate charge simply doesn't change. QG prime is equal to QG, because VG prime must be equal to VG. Conclusion: the effect of having mobile charge at the gate oxide interface is absolutely zilch. There is no effect whatsoever. Okay, now let's take a look at the second case number 2, where we take this mobile charge, this positive mobile charge, or I should say an impulse of positive mobile charge, and we're going to move it onto the oxide silicon interface. And of course, the way we do that is to change the gate voltage. And just going back to the original picture, put a double arrow here, which just confirms or denotes the fact that the charge can move between one interface to the other interface. If the gate is negative, I would expect that this positive impulse would be over here. A negative gate voltage is associated with NMOS with accumulation. A positive gate voltage, where the mobile charge would move to the other side, to the oxide silicon interface, would be associated with inversion. So over here, this is for NMOS, we have a situation where accumulation, if the Q sub M is over here at the oxide silicon interface for NMOS, we would generally associate that with inversion. And the opposite would be true for PMOS. For PMOS, gate voltages are positive, and the oxide charge would be at this interface, and in inversion, the oxide mobile charge would be at the gate silicon interface. And our analysis here will be a little bit more quantitative. This was a qualitative reasoning which may or may not be satisfying. Now we're going to do a little bit more qualitatively. And instead of saying we're at threshold, we're going to start with flat band. So at flat band, we have a gate voltage equal to some voltage, it's called the flat band, in which I produce a situation. The situation is produced in which all the bands are flat. There is no charge here, there is no charge here, there is no charge in the silicon. And again, this could be P or N-type silicon. So if we start with our default structure with a doping of 10 to the 17th for P silicon and an N plus gate, we found that the flat band voltage was about minus 1 volt. Actually, to be precise, it's minus 0.98 volts. No, it's not terribly important. Okay, now we're going to add an impulse. So previously, no impulse. Then we say, okay, let's put in an impulse of Q sub M right at the gate. Well, if we have charge right at the gate, a positive charge right at the gate, we damn well better have negative charge right at the gate also, because all positive charge induces a negative charge. There are lines of force right between the blue and the red line, and the positive charges on the red line are attracting or sucking up negative charges so that they can end, the lines of electric field can end on a negative charge. Well, there's lots of negative charge in the gate. It's a metal. So basically all we're doing here is we're sucking up negative charge from the gate so that we have a negative impulse, G sub C, which exactly counterbalances the positive impulse of Q sub M. So if we draw a box around them, this is called a Gaussian surface, we will have electric lines of force here, but there is no electric lines of force, and there is no enclosed charge if we are to the right of the red impulse charge, Q sub M. So there is no electric field here, there is no electric field here, all bands continue to be flat. The only effect was to suck up some negative charge from the metal gate. And since there's an inexhaustible supply of electrons on the metal gate, that's pretty easy to do. So that's an indication of the fact that there is no effect whatsoever for this Q sub m if it is located at the gate oxide interface. And that basically is the same result that we got with this much more qualitative and perhaps not quite as satisfying approach that we took previously. Okay, now we're going to move the mobile charge to the oxide silicon interface over here. So now what do we have? Well, in this particular case, we have a positive Q sub m here, and let's consider P silicon or NMOS. And so what happens here is, because the Q sub m is located at this interface, what do we have in the P silicon? Well, we have minority electrons, which are mobile, but we also have negative fixed ions, which are immobile. And what we can do here, what is done here, is because the Q sub m is right at this interface, right next to these fixed ions, what it will do is it will uncover negative fixed ions to balance the effect of the positive Q sub m. So now we're going to have, well, we're going to have band bending, and the bands would bend up if it's N silicon or down if it's P silicon. Since we're assuming P silicon here, we're going to say that the bands will bend down, and they will bend down just enough so that we have enough uncovered negative ions to balance the positive Q sub m. Well, if the bands bend down, we have a voltage change on the gate. The gate must counterbalance that, and we have a delta VG. We're no longer at flat band. We were at flat band, but flat band implies or requires that there is no band bending. Once we have band bending, in the case of P silicon, the band's bending down, we are not at flat band anymore. And now I say, what is the voltage that will restore flat band? That is this delta VG, which we're going to have to apply to the gate in order to restore flat band, and it is a negative voltage, which will induce a negative charge. So now we draw our Gaussian surface, and we ask how much charge is enclosed in this surface, minus Q sub m. And if I extend this dotted line all the way to the right until I get right to the interface, it is still minus Q sub m. Therefore, since it's negative, I have a negative electric field. Electric field lines point from right to left. So let's examine this delta VG a little bit further. We know it's charge, minus Q sub m. It's just enough to compensate for the band bending down in P silicon. And we can write it as, well, it is all voltages are charge divided by oxides. And that's exactly all we're saying here. A delta VG will result in resulting from a Q sub m will equal to, it's minus because the bands bend down and I have to compensate for that. And it's just equal to minus Q sub m divided by C ox. So now the new gate voltage, which is a new flat band voltage, is equal to the old flat band voltage, minus 0.98 volts, plus this delta VG. And this is the expression right here. Hopefully it all makes sense. The minus sign comes from the fact that we had to change the flat band voltage, and changing the flat band voltage induced a negative minus Q sub m at the gate oxide interface. And perhaps we should at least point out the fact that I didn't have to start at flat band. I could have started a threshold or depletion or whatever, and it would have basically been the same thing. If this impulse of charge is added at the oxide silicon interface, this is the change in the gate voltage. Two notes of perhaps interest. One is if I put this oxide any place in here, it doesn't matter where, I'm going to get an electric field to the right, or I should say to the left of where I put it. So if it's, for example, right at this point here, everything to the left of that will have an electric field. There will be some band bending, therefore, in the oxide. So I'm always going to get some band bending due to the fact that I have a Q sub m, except if the Q sub m is at the gate oxide interface. Okay, the other thing is, if we compare NMOS and PMOS, in NMOS, I'm going to have an inversion. I'm going to have a positive voltage on the gate, and therefore the Q sub m will be indeed at the oxide silicon interface, and that's where it has the most effect and does the most damage. On the other hand, in PMOS, where I have an N silicon substrate, inversion will have a negative charge generally on the gate, and the plus Q sub m will be at the gate oxide interface, where it does no damage. So chalk one up for PMOS rather than NMOS. So just to do an example for our default structure, N plus gate, P silicon doping of 10 to the 17th, where I have a Q sub m of 10 to the 12th, that's pretty high. This should be a superscript, by the way. Let's see what the change in the flat band voltage is. The old flat band voltage minus 0.98. Q sub m is 10 to the 12th, multiplied, of course, by the electronic charge. So this is the coulombs on the numerator, and Cox in this particular case. This is a very thin gate oxide, typical of what we have today, but still pretty darn thin. And we get a change of about 0.1 volts, which is about 10%. So I increase the flat band voltage in magnitude from 0.98 to minus 1.08. So just to summarize again, when the mobile charge is positioned at the gate oxide silicon, the left side, it has no effect because electrons are drawn off the gate, an inexhaustible supply of electrons, and we don't change the silicon or the oxide band bending at all. However, when the impulse is located at the oxide silicon interface, electrons are drawn off the silicon, and that does change the silicon and or oxide band bending. Okay, so there's a little story associated with this I'd like to share. There's three types of charge. Actually, there's four. The mobile, the fixed, the interface. There's two types of fixed charges here. One is called fixed charge, the other is interface charge. We're going to be looking at interface charge. And there's a fourth type where we can have some fixed charge located inside the oxide at an arbitrary point. But once we've got it located over here, we figured out that one, and we've figured out the case where it's located on the other side. The one, if it's located anywhere, it's in the middle and it's fixed, that's just a relatively straightforward special case. So we can say without too much loss of generality that there's really only three types of charge. The mobile charge is the most historically interesting one because it's so capricious. We never know where it's going to be. It could be on one end, it could be on the other end, it could be in the middle, it could be all over the place. Now, field effect transistors were around, at least theoretically, even before bipolar transistors were around. The original patents or field effect transistors, I believe, go back to the 1920s. The idea was somehow you could control the channel by using an electrical charge. Nobody knew how to do it, but at least there were some ideas that it might be an interesting way to make a solid-state device. Now, the first real serious efforts in making field effect transistors out of silicon really did not occur, I believe, until the late 50s, early 60s, and they couldn't make the darn things work. The yields were terrible. They didn't understand how they worked. They were supposed to work a certain way, and the theory and the practice, the observation, just didn't match. So everybody was just up in arms. They couldn't understand it. And the most difficult part was sometimes it worked. It worked reasonably well, but most of the time it did not work at all. So the question was, how do we try to understand what's going on? And they narrowed things down to the gate oxide. The gate oxide was the thing that was really causing problems. Now, it's important to note that in those days they weren't talking about a gate oxide of 20 angstroms. They were talking about a gate oxide of 1,000 angstroms, perhaps, say, instead of 2 nanometers, 200 nanometers. Very thick gate oxides. And they at least narrowed it down, and they said the probable cause of all of these terrible effects, poor yields and lack of understanding, revolves around the gate oxide. And this was something that's even more perplexing today, because the greatest minds of that era, including the great Bill Shockley himself, and I say great with quotes because he had some personality issues, but they were not able to understand this. So here's another little fact. It seemed to work out that it was even more mysterious, that it depended on the time when the gate oxide was grown. And we'll talk about growing of gate oxides in just a little bit. It worked out that if the gate oxide was grown in the morning, the results were reasonably good. If it was grown in the afternoon, the results were terrible, specifically if it was grown after lunch. How could that be? That is completely inexplicable. Well, anyway, as the story continues, a team of experts was gathered together, and they're trying to figure out what kind of correlation is there between the time of oxide growth and the shifts in the CV plots on the poor yields. And it was shown conclusively that oxides grown in the afternoon exhibited the most severe shifts and the most deleterious effects in device performance. So now they had their smoking gun. And it became clear, after a lot of head scratching and hair pulling, that the culprit was indeed small mobile ions, specifically sodium ions, and these sodium ions were introduced by people that were loading the wafers into the furnace who had sodium on their hands. The sodium on their hands was because they were not wearing gloves, and they had recently eaten potato chips, and potato chips have lots of sodium. So by improving the cleanliness and presumably not outlawing potato chips should be outlawed, but not because they induce sodium into silicon wafers, just because they're not particularly healthy. I would outlaw them, but I would reduce their consumption. The problem that baffled Shockley and his very brilliant co-workers was finally solved. So that's the story. I believe there's some degree of truth to that, of how potato chips almost destroyed the microelectronics revolution. And I think it's again important to emphasize the fact that we're not talking about 2 nanometers here. We're talking about 200 nanometers. So if you go back here, that C oxide is going to be reduced, not increased, but reduced because of a large gate oxide by at least an order of magnitude, or maybe even 2 orders of magnitude. So this guy is not 0.1. This could be 10. It's going to be a huge, huge effect. So we're tempted to think that with the advent of greater cleanliness, wearing gloves, perhaps not eating potato chips before one loads the wafers into the oxidation furnace, that the issue of the mobile charge would have gone away. That, unfortunately, is not what was observed. And the problem revolves around this interface, the interface between 2 different materials, in this case silicon and oxide on the left. Whenever we either grow or deposit one material on top of another, all kinds of dangerous things can happen. Specifically, we can have contaminant atoms which come into the growth process or the deposition process, or we can have dangling bonds which don't have counterparts. In this specific case, we'll have dangling silicon bonds which are not filled. So we can have what we call trapped or interface charges right at this interface. And the difference between trapped charges and mobile charges is that the number of traps, the number of charges at the interface varies according to the position of the Fermi level. So that's what we want to talk about now. And we'll do that with a number of energy band diagrams. We start with an energy band diagram which has what we call deep donor states. Shallow donor states, the donor level would be right up here, about 60 to 80 millivolts below the conduction band. If it's a deep donor, the donor state would be somewhere close to or at midband. And what we're going to say is, and we're going to show this in a little bit more detail later on, that for those states above the Fermi level, these states would be unoccupied. And when I say unoccupied, they're unoccupied by an electron. The donor has an electron to donate, and when the donor atom donates the electron, it becomes unoccupied by the electron. It becomes empty again of the electron because the electron has been donated to the conduction band. Well, it was neutral. If it donates an electron, it becomes positive, and that's shown by these red-filled circles. If the state is below the Fermi level, the state is occupied by an electron. It is neutral and is filled, again, filled by an electron. So this represents donor atoms which have a donor state which is at or close to midband. So let's look at that in a little bit more detail in the more conventional donor atom, which would, for example, be phosphorus. This is drawn a little bit, not to scale. This donor state probably should be a little bit closer to the conduction band. But the point is that if the Fermi level is below the electron state, which is shown here, then there is a driving force represented by this arrow, which pushes the atom, in this case phosphorus atom, to donate an electron. If, however, the Fermi level rises above, so the Fermi level is up here, then the donation pretty much stops. And that's exactly what we're showing here. As the Fermi level is above the electronic state, then the atoms are neutral. If the Fermi level is below the electron states, I would add more of these positive fixed red-filled circles. So if the Fermi level falls, more red circles. If the Fermi level rises, more unfilled circles. And that's exactly what is shown here. The electronic state stays constant, Fermi level rises up to here, the donation stops, the Fermi level is below the electron state, and then there is donation, and there are positive fixed ions. Okay, so now we go on to the acceptors, and if we have the donors where the ions are on top, we expect that the acceptors, the ions will be on the bottom, because for acceptors, everything is reversed. And we're going to have a deep acceptor state, again, right at mid-band. Let's take a look at that. So here we have, again, the acceptor ions. These are the guys that have accepted an electron. They are full. They are full because they have accepted, and they are negative. They were neutral, accepted electron, now negative. The unoccupied or empty or neutral states that have not accepted an electron, they're the guys on top. So we notice it's exactly the reverse of the donor. And we can see in the summary of the energy band diagrams, let's first look at the donors. The donor state is indicated here in red. So if the Fermi level is below the donor state, that's the quote-unquote normal situation, then we have a donation. If the Fermi level is above the donor state, we do not have a donation, exactly as we're showing here. Fermi level high, no donation. Unfilled circles, Fermi level low, donation, red, positive ions. Same thing happens for the acceptor. In this case, if the acceptor level is above the Fermi level, we do not have ions. That is this case up here. And if the Fermi level is above the acceptor state, then we do have acceptance and we have positive ions. Did I say positive ions? We have negative ions. So that's okay. And that is covered completely in one big picture right here. So let's see if we can understand this a little bit better, because this has basically everything included, and it's the key to finding out or figuring out why this is not a good thing to have interface trop states. This is the donor part. This is the acceptor part. So if the Fermi level moves up, then I have more of the red circles. If the Fermi level moves down, I have more of the blue circles. And that basically tells the whole story. So now let's look at the CV plot for an NMOS structure. So in NMOS structure, I have P silicon in the bulk. The Fermi level is close to the valence band. In accumulation, it's even closer to the valence band. I have a negative voltage on the gate, and this would be an energy band diagram for the NMOS structure. In accumulation, the bands bend up a little bit, so the Fermi level is, it should be even a little bit closer, but it's reasonably close. It's certainly below intrinsic. Intrinsic is up here, so it's close to the valence band in the bulk. It is really, really close to the valence band in accumulation. So the Fermi level has gone down, and if the Fermi level goes down, what happens? Well, we can see that from figure 2218. Fermi level goes down. I have less of these guys. These guys become, this guy, for example, will become a neutral unfilled circle, but this guy will become a red-filled positive circle. So I have a positive Q at the interface. That's exactly what we had when the mobile charge distribution was at the interface. The mobile charge distribution was positive. When it's at the interface, it has a maximum effect. And that is what is shown here, except I replace the Q sub m by a QIT. So we have a negative shift in the flat band. Flat band moves to the left, and that's kind of important. Well, we're generally not interested in accumulation. That's kind of a boring structure. But really, we want to go into depletion and inversion. So in depletion and inversion, the gate becomes positive. The Fermi level moves up toward the conduction band. And as the Fermi level moves up, we have less of these guys and more of these guys. We have lots more negative ions, which are covered. All these guys now start to become filled blue minus circles, and these guys basically go away. So the Q becomes positive, and now the threshold voltage, which because we're in the inversion side of the diagram, the threshold voltage shifts and becomes more positive because the QIT now is what is it, negative or is positive? Well, I'm going back here. As it goes up, it becomes more and more negative. So if the QIT becomes negative, this becomes positive. The threshold voltage now increases, and that shifts the CV plot to the right. And that is shown here, and we can understand from this diagram why this is really detrimental to device performance. What we have with an interface trap charge, we have a shift in the threshold, in the flat band voltage, the flat band voltage shifts from this point to this point, shifts to the left, whereas the threshold voltage, which was over here, shifts to the right. It becomes stretched out. So what that means is, and this is again just for illustrative purposes only, I think you can figure this. Actually, I'm not even quite sure whether I have this in my notes, but you can actually do some calculations here. They're a bit rough, perhaps, but this is the region that is bad. This is the weak inversion region. This is the region we want to make as small as possible. This is the point, for example, this would be intrinsic to close to or at threshold. So the weak inversion region, if we have no interface traps, would be the points from here to here. If we do have interface traps, because the threshold is now shifted from this point to this point, the weak inversion region has stretched out, and that causes a very severe deterioration in the device performance, and we see that on the CV plot, and we say, "Eek, that's not so good." Well, how do we deal with this in practice? Well, people said, okay, these are dangling bonds. How do we undangle the bonds? Let's put a molecule, not a molecule, an atom in there, which can attach to those bonds. So what people do is they do an anneal, a high temperature process, where they put in hydrogen gas, and the hydrogen attaches to any dangling silicon bonds. And what we find with the hydrogen anneal is that the red curve goes back to the black curve, and that is how this problem has pretty much been taken care of. So let's at least start our discussion on the actual growth. How do we make this oxide? And we're going to be looking at the Deal-Grove model of thermal oxidation. And the chemical reaction at the silicon interface is pretty easy. You just have your silicon. It's in oxygen. It's in air. It could be air at room temperature even. This is a one-way arrow. It is not an equilibrium reaction. There is no breaking up of the SiO2 into its components. It only goes from left to right, and it's a relatively simple reaction. And if we take a look at this is a bare silicon wafer, and you say, well, that's in room temperature, I would expect there would be, well, silicon. and you would be, unfortunately, not right. This is silicon, that's true, but on its surface there is a very, very thin layer of oxide, and we can show that. And we can show it by taking a voltmeter and placing leads of a voltmeter anywhere along the silicon, doesn't matter where, and if we do it gently enough, we don't want to scratch this gentle oxide that's on the surface, but if we do it gently, we'll find we get an open reading. Silicon dioxide is an insulator, so because we get an open reading, there is something on the silicon which basically insulates it. There's another way to do this, which is to remove the glass. So you can, I should say before we do that, there's another way to show that we do have an oxide layer on the silicon, and that's by spraying water. And you'll notice if you do that on a silicon wafer, and I've done this many times in class, the water will spread out over the silicon because glass is hydrophilic. So that's another way to show that there is indeed an oxide layer on the silicon. There is another way to show this, which shows it in a much more convincing manner, but as they say, do not try this at home. I do it in class. I don't tell anybody. That's because it's not very safe. Anyway, you take hydrofluoric acid, HF. You can dilute it. We generally dilute it down for this experiment to 100 to 1. It generally comes about 10 to 1. I dilute it down to about 100 to 1, but it's strong enough. It's quite dangerous. So again, don't do this at home. But what I do is I'll take a Q-tip and I'll take part of the wafer, say this part over here, and I will rub HF over this part of the wafer, basically dissolving the glass. And then what I do is I spray water, and I'll notice that where I have the glass, we get a nice smoothing out of the water. It spreads out very nicely. But where we have the silicon is hydrophobic, so the water beads up. And that is a very graphic way to show that we do have a SiO2 layer on the silicon, because when we get rid of it, we don't have it. And then what I'll do is leave it sitting on the table someplace, and then come back in about a half hour or so, respray the water, and you will notice at that point that the entire wafer becomes, again, hydrophilic, because even in a matter of 10 to 15 to 20 minutes, I get a layer of oxide on the silicon. So the model for oxidation, or growing an oxide of any given thickness, for example, I want 2,000 angstroms of thermal oxide, or I want 20 angstroms of thermal oxide. I want to know at what temperature and how long I have to perform the growth process. That particular model is called the Deal-Grove model, named after Bruce Deal and Andy Grove. Of course, we met Andy Grove previously. He was the CEO of Intel for many years and a very important semiconductor scientist. So this is a picture of a furnace. These are the wafers which are being loaded into the furnace. This is the furnace. The growth process takes place at about on the order of 1,000 degrees centigrade. And it's typically done at atmospheric pressure. So this is the cartoon of what we'll be looking at, which describes the Deal-Grove model. And we have essentially 1, 2, 3, 4 basic parts to it. We have, this is the atmosphere, this is the ambient out here before we load the wafers. As we load the wafers in, of course, the temperature goes up. So at this point, when the wafers are loaded into the furnace, we still have an atmospheric situation, and we have a concentration which is Cg. So if we look at this a little bit closer, what we have are 1, 2, 3, 4 concentrations. And these C's refer to the concentrations of oxygen. And notice that they decrease as the process moves from left to right. So once the wafers are in the furnace, we are in this region here, and this region is basically we call it the stagnant layer. It's oxygen, which is dissolved in liquid SiO2. There needs to be a concentration gradient which drives the oxygen from purely atmosphere to this layer right here, where we start the actual growth layer of SiO2. This is glass. This is solid SiO2. However, the oxide does not grow here. Oxygen is pushed in to the growth layer, diffuses through the growth layer until it gets to the silicon layer. There's no way I can grow glass on SiO2. I need to grow glass on silicon. So the reaction takes place here, and we'll see it's the simple reaction. Silicon plus oxygen equals glass. It's a first order reaction because it is controlled only by the concentration of oxygen at the surface. We're assuming we have an inexhaustible supply of silicon. Okay, so there's actually 3 different fluxes. Flux moving into the stagnant layer, and then the flux moving from the static layer into the growth layer, and then finally in the growth layer itself. All these fluxes must be equal, because if they're not, then we get pileups. So there's a continuous process flow from purely ambient, which is the highest concentration of oxygen, to the lowest concentration of oxygen at the diffusion layer, when the oxygen can no longer diffuse through the growing oxide layer, either because the temperature isn't high enough or the oxide layer is simply too thick. Then the growth process stops. So there's a couple of really important constants, namely how much oxygen can we cause to dissolve in the SiO2 layer. The oxygen's got to get into here. Here it exists as a gas. Here it exists as a solid. So we have a gas-solid interface, and the law which governs that is called Henry's law, and we'll talk about that a little bit later on, but just as a preview, it says that the higher the concentration of oxygen in the gaseous stage, the more I can push in to the solid stage. And that makes sense. And we'll see an animation of that. And the other thing is the diffusivity, the diffusion of oxygen through the growing glass layer. So the equation that comes out of this, pops out at the end, involves something called Henry's constant, the diffusivity, and of course the starting concentration of oxygen. So we'll have 3 main constants: Cg, H, Henry's constant, and diffusivity. And of course, driving the whole thing is temperature. So we'll have 4 actually main parameters, temperature probably being the most important of the 4. Okay, so let's end here and jump down to the last slide. So we covered charge and gate oxide, trapped interface charge, smearing of the CV plot, why that's bad, because it, certainly one reason is that it expands the reconversion region, which is really, really bad. We want the reconversion to be as nondescript and as trivial as we possibly can make it, because that's what causes your laptops to heat up. So anything that adversely affects the reconversion, which is to say makes it bigger or better, is not good. We started on the Deal-Grove model, so next time we will plow through the Deal-Grove model and then touch on some of these other issues. These are not particularly complicated, and they're more or less a review of everything that we've learned. And hopefully we'll have time for some worked problems. And we close today's session with the Triumphal March from Aida, and we'll see you next time.